Today I will be talking about wind energy, one of the most important source of renewable energy in the world. Wind is something we experience every day, but did you know that is natural movement of air can be used to produce electricity? Yes. Wind has a lot of energy in it, and with the help of technology we are able to convert that energy into electric power that we use in our homes and industries. Over the past few decades, the world has been facing many problems due to the use of fossil fuel like pollution, climate change, and limited resources. So, scientists and engineers started looking for clean and renewable alternatives, and one of the most successful solution has been wind power. In fact, today more than 83 countries are using wind energy. For example, Denmark produces around 40% of its electricity just from wind farms. Wind energy is not new. People have been using wind for hundreds of years. For example, to sailboat, pump water. The idea of using wind to generate electricity started in late 1800s. In this presentation, we will take a look at the history of wind energy, how works, and how it is helping us build a cleaner and better future. Do you know when the wind energy evaluation started? The history says during the second half of the 20th century, there was a risk in the environmental toll of fossil fuel depends, and hence there was a rush to develop clean renewable sources of energy. One of the foremost among these clean energy technology has been wind power. Today, over 83 countries make use of wind power, with Denmark using 40% of their electricity from wind farms. Charles scientists discovered the wind energy. You can see on the right side pic the first automatically operating wind turbine generator, 20 kilowatt, having 70 m rotor diameter, which ran for 20 years to charge battery. This slide shows the image of the first wind turbine developed in 1888 with set-up gearbox to run DC generator. Do you know which country first used wind energy? In early days, people used wind energy to propel boat in the river Nile. This energy is also used to pump water and to grain in the country Persia, now is called Iran, and the Middle East. This slide shows how wind is converted to electrical energy and transmitted for over usage. So now you all know wind is primary source of energy. Movement of air in the atmosphere is the wind. We feel this movement carry kinetic energy which converted to electricity when connected by the wind turbine. To calculate the power, wind, horizontal speed and direction are taken and measured by using anemometer. What makes wind? During the day, air above the land heats up faster than air over the water. Warm air over the land expands and rises, and heavier Cooler air rushes in to take its place, creating wind. At night, the wind are reversed because air cooled more rapidly over land than does over the water, and that's how the wind are generated. In the globe, we can see equatorial and tropical region, it is close to the near equator, get the maximum heat from the sun, hence they get hotter than polar region. The air surrounding this region gets heat up and rises to create the vacuum. Cooler air from the pole rushes to fill the vacuum. The wind does not flow in the north-south direction because a change in direction is caused by the rotation of the earth. Now let's see how a wind turbine works. In flow of wind, rotate rotor A and blade B. This rotor and blade spin and shaft C and gearbox D, which spin the generator Z to get electricity. In use, we find two types of wind turbine. One is horizontal axis and another one is vertical axis. The advantages and disadvantages of vertical axis turbines are: vertical axis turbine advantages: it is omnidirectional, accept wind from any direction, compounds can be mounted at ground level, and lighter weight tower can theoretically use less material to capture the same amount of wind. And disadvantages of vertical axis turbine: rotors generally near the ground where wind is poor, centrifugal force stress blade, poor self-starting capabilities, requires support at top of turbine rotor, overall poor performance and reliability. Horizontal wind turbine are classified as small, intermediate, and large based on the power. They produce less than 10 kilowatt or small turbine use home and farm usage. Intermediate are between 10 to 250 kilowatt using for powering the village and hybrid system. The large turbine are range from 250 kilowatt to 2 megawatt used to power the central station wind farms. As already explained about the wind turbine, now let us see the efficiency of turbine. Generally, the turbine blade rotate between 13 and 20 rpm depending on the technology. At a constant or variable velocity, the velocity of rotor varies with respect to the velocity of the wind to reach a greater efficiency. The average turbine life is 25 years. Now let us have look on the wind turbine. The basis wind energy conversion device in the wind turbine. The main component of wind turbine for electricity generation or foundation, tower, nacella, rotor, transmission system, generator, yaw and control system. Foundation. A wind turbine must have a strong foundation to withstand strong wind and support the overall height and the length of rotor blade. The rotor, the rotor converts kinetic energy of the wind flow to mechanical energy. The rotor can have three blades or two blades. Generator. A generator converts mechanical motion of rotor to electrical energy. It works on principle of electromagnetic induction. When a conducting coil rotates in a magnetic field, Voltage is generated across the coil terminal, which became source of power. Gearbox. Wind turbine rotate typically between 20 rpm and 400 rpm. Generator typically rotate at 1200 to 1800 rpm. Most wind turbine require a setup gearbox for efficient generator operating. Next, tower. Power generation equipment is kept in the tower. Further, it is across to the nacelle and rotor. Nacelle is the heart of the turbine. It includes the part, namely the generator, gearbox, and turbine drive. Blade. The blade design uses lift, the creation of the high and low pressure zone from the wind to move the blade. The rotor, the portion of the wind turbine that collects energy from the wind is called the rotor. The rotor usually consists of two or more wooden fiberglass, it is a new design, or metal blade which rotate about an axis, horizontal or vertical, at a rate determined by wind speed and the shape of blade. The blade are attached to the hub, which in turn is attached to the main shaft. Generator. The generator converts the mechanical energy of the turbine to electrical energy. Inside this compound, coil of wire are rotate in a magnetic field to produce electricity. Different generator design produce either alternate current or direct current available in a large range of output power rating. Generator that produce AC current are generally equipped with features to produce the current voltage, that is 240 volt, and constant frequency of electricity, even when the wind speed is fluctuating. Transmission. This is used to transmit the mechanical power generated by the blade to generator. The number of revolutions per minute of the wind turbine rotor can range between 40 rpm and 400 rpm depending on the model and wind speed. Generator typically require rpms of 1200 to 1800. Some DC type wind turbine do not use transmission. Instead, they have a direct link between the rotor and generator. These are known as direct drive system. Blade and
What is a wind turbine and how does it generate electricity? Wind power, components, accidents. Wind turbines are devices that convert the wind's kinetic energy into electrical energy. We can simply describe the wind as moving air, caused by differences in atmospheric pressure between different regions of our planet. Differences in atmospheric pressure arise as a result of temperature differences. When the air moves from a high-pressure region into a low-pressure region, we feel the moving air as wind. On the other hand, we can describe wind energy as the process in which wind is used to generate mechanical energy or electricity. Since the beginnings of civilization, man has always took advantage of wind energy, from the simple sailboats to the grinding of grain with windmills, up to the actual production of electricity thanks to the wind energy converters, also known as wind turbines. There are different types and different sizes of wind turbines. In this video, we will focus on the most common horizontal axis turbines. We'll find out which are the main components of this particular type of wind turbine. We will understand how these devices are able to transform wind energy into electric current. We'll see why wind turbines don't have more than 3 blades through the observation of their airfoil shape. and we will also see what are the main causes of accidents that occur during the operation of these devices. The first wind turbines were built towards the end of the 19th century with the aim of supplying electricity to small, isolated villages. In the following years, the gradual structural and technological improvements of these devices allowed the creation of real wind farms entirely dedicated to the production of electricity. Nowadays, there are about 26 companies in the world specialized in the production of wind turbines. JAES, besides being a qualified partner for some of the most important wind turbine manufacturers, is constantly engaged in the supply of all those spare parts necessary for the production, assembly, repair, and maintenance of wind turbines. As we already mentioned at the beginning of this video, wind turbines transform mechanical energy into electrical energy. The wind energy caught by the wind turbines is in fact transferred thanks to a mechanical shaft to a generator. The generator transforms the rotation energy into electrical energy, which in turn is transferred to a transformer, usually placed at the base of the wind tower. The transformer acts as a link between the wind turbines and distribution grid. It steps up the low output voltage from the generator to higher distribution voltage level. Let's take a look at the various components of a wind turbine. This is the tower, one of the most important parts. It represents the supporting structure of the wind turbine and has the function of absorbing the vibrations generated by the rotary motion of the blade. These are the blades, which are aerodynamically optimized to capture the maximum power from the wind and transfer it to the rotor hub. Each blade is usually 20 meters or more in length, depending on the power level. The rotor is the rotating part of the wind turbine. The rotor hub holds the wind turbine blades while connected to the gearbox via the low-speed shaft. Here, we can find the pitch control system. Thanks to the pitch control, blades are turned in their longitudinal axis to change the angle of attack according to the wind directions. This mechanism also blocks the rotation of the rotor when the wind is too strong or too weak. The nacelle is instead the enclosure of the wind turbine that houses all of the generating components, including the gearbox, the braking system, and the generator, but also the pitch control system and the yaw system, which is responsible for the orientation of the wind turbine rotor towards the wind. An anemometer placed at the rear of the nacelle, in fact, constantly detects the wind direction. Whenever there's a change in wind direction, the anemometer sends a signal to the yaw system that provides to rotate the entire nacelle and consequentially the rotor and the blades to meet the wind at the best angle. But now, let's see in detail what happens when the wind turbine goes into action. The blades start to turn when the wind reaches the so-called cut-in wind speed, that is, the point at which the turbine starts generating electricity from turning. The rotor is connected to the drive shaft, which rotates inside the nacelle. The rotational energy of the drive shaft is transformed into electrical energy by the generator. A generator is in fact a device that uses electromagnetic induction to produce electrical voltage. One of the main elements of the power transmission of the wind turbine is the speed multiplier. Since the rotor blade rotation is low, the speed multiplier inside the gearbox is used with the aim to reach higher levels of the rotational speed needed by the electric generator in order to produce the electrical power. Most wind farms are also equipped with inverters that convert direct current into alternating current at 220 volts, making it suitable for grid feeding or self-consumption. If the wind speed increases, there will be a gradual increase in the instantaneous power of the turbine until reaching the rated wind speed, that is, the wind speed in which the generator reaches its rated power output. As the speed increases above the rated wind speed, the forces on the turbine structure continue to rise and, at some point, there is a risk of damage to the rotor. As a result, the braking system is employed to bring the rotor to a standstill. This is called the cut-out speed and is usually around 25 meters per second. We've already said that the turbine's blades start to turn when they're hit by the wind. If we look closely, we can notice that the blade has a lot of airfoil cross-sections consisting of different sizes and shapes from the root to tip. The teardrop shape of the blade is very similar to the aerodynamics of the wing of the aircraft, which we've already discussed in our previous video. In that case, the airflow hitting the wing followed precise trajectories, allowing the molecules of the lower surface to have a higher density than those of the upper surface. The difference in pressure between the two parts allowed the wing and consequentially the whole aircraft to lift up. Also in this case, the lifting process of the wind turbine blades is very similar. Thanks to the pitch control mechanism, the blade is tilted in order to be always aligned with the airflow. When the blade speed is increased to the tip, the relative wind speed becomes more inclined towards the tip. This means that a continuous twist is given to the blade from the root to the tip. By observing the operating principle of wind turbines, we may be led to believe that a turbine with many more blades is more powerful than one with 3, 2, or even a single blade. This conclusion has some truth. More blades allow you to achieve more power, but the more blades there are on a wind turbine, the higher will be the torque, which is the force that creates rotation, and the slower the rotational speed because of the increased drag caused by wind flow resistance. So, a wind turbine with many blades will be more powerful but less efficient than one with less blades. A wind turbine with 3 blades placed at 120 degrees from each other represents a good compromise between power and efficiency. A turbine with 4 blades means more weight and therefore more costs. Also, a wind turbine with 2 blades will obtain similar performances but would require bigger dimensions and therefore higher costs. We have seen so far that the design and implementation of a wind turbine involves a series of structural choices that are not directly linked to the power of the wind turbine, but take into account factors such as costs, maintenance, noise pollution, landscape assessment, and many others. Maintenance still represents a fundamental element for the correct functioning of these devices. Unfortunately, many accidents still occur if regular maintenance activities are not carried out. The causes of these accidents can be mainly attributed to fires related to the malfunctioning of internal components or lubrication system, damage caused when foreign objects make impact with the blades, bad weather conditions or thunderbolts. Finally, if you found this video useful, let us know by leaving a comment and subscribing to our YouTube channel to stay tuned on the latest release of new videos. Thanks for watching.
Blade and its design is important for wind turbine. The determination of number of blade involves design consideration of aerodynamic efficiency, compound cost, system reliability, and aesthetic. The aerodynamic efficiency increases with the number of blade, but with a diminishing return. Increasing the number of blade from 1 to 2 yield a 6% increases in efficiency, whereas increasing the blade count from 2 to 3 will yield only an additional 3% in efficiency. Generally, the lesser number of blade, the lower the material and manufacturing cost. The rotor which an even number of blades will causes stability problems for wind turbine. What is the reason? When the uppermost blade bend backward because it gets the maximum power from the wind, the lowermost blade passes into the wind shared in the front of tower. This produces uneven force of rotor shaft and a rotor blade. Let's have a study on the blade design. Attach a red ribbon to the tip of the rotor blade and yellow ribbon about 1/4 of the way out from the hub. At constant speed, the rotor blade moves through the air at 64 meter per second, while at the center of the hub it is 0. At 1/4 of the hub, the speed will be 16 meter per second. The yellow ribbon close to the hub will move back of the turbine. Then the red ribbon at the tip of the blade. This is because at the tip of the blade, the speed is 8 times higher than the speed of the wind hitting the front of the turbine. The rotor blade will twist to get higher steeper angle to move the blade during the wind pass over. The rotor blade will stop, giving a lift if the blade is hit at the angle of attack, which is too steep. Therefore, the rotor blade has to be twisted so as to achieve an optimal angle of attack throughout the length of blade. This slide shows the lift design of the blade. A wind speed and pressure differential is created between the upper and lower blade surface. Will lift the blade and translated into rotational motion. Will show the importance of blade design of wind turbine. The following are the range of wind speed 0 to 10. The wind speed is too low to generate power, hence the turbine will stop and rotor is locked. 10 to 25. 10 as the minimum operational speed is called cut-in speed. In 10 to 25 mph, wind generate power increase with the wind speed. At 25 to 50 mph, wind turbine reach the rated power. It is the maximum operating power. If the wind speed is greater than 50 mph, the turbine is shut down to prevent structure failures and is called cut-off speed. The wind turbine generate electricity. Now let us understand the turbine structure and its mechanism. Towers, lactic, guide pole, concrete and tubular steel towers. Yaw mechanism is important for wind turbine to rotate the system against the wind direction. If the turbine is not perpendicular to the wind, then the power flowing is lower. Wind turbine running the yaw error are running at the high factive load. About braking mechanism. It is important for turbine stop during the emergency. These are two types of braking: aerodynamic braking system and second one mechanical braking system. Aerodynamic braking system will turn its blade to 90 degree at longitude axis. They are spring operated and thus work even in the case of power failures. Whenever the speed of the wind is high, The following principles are applied to the blade to stop the turbine: stalling, pitch control, flaring. Let us understand one by one. Stalling is the principle applied in the turbine blade during the increased angle of attack of the wind result in decreasing lift of the blade. Here the motor turn the blade towards stall when wind speed are too high. Disadvantages. The first one, the stalled blade causes large vibration and therefore noise. Second, the aerodynamic power on the blade is limited. And third one, lower efficiency at low wind speed. Pitch control is another principle applied where there is decreasing the angle of attack resulting in the decreasing of lift. Here the blade rotate out of the wind when wind speed are too high. The flaring principle, the blade axis are moved out of the wind direction to decrease angle of attack and cross section. Image shows more about flaring principle. It's about wind farms. Same thing. About wind farms, a wind farm is a group of wind turbines in the same location used for producing of electric power. Individual turbines are interconnected with the medium voltage power collection system and communication network. At a substation, the medium voltage electrical current is increased to the high voltage with the transformer. A large wind farm may have a few dozen of several hundred individual wind turbines. The wind farms may also be located offshore to take advantages of strong wind blowing over the surface of ocean. Following are the factors affecting the wind turbine: location, wind speed, wind park effect, environmental and aesthetic impact, and effect on power grid. Those are types of wind turbine: onshore, nearshore, offshore, airborne. Onshore. Onshore turbines are installed in a hilly or mountain region. They are normally located 3 kilometers or more from the nearest shoreline. Nearshore. Nearshore turbines are installed on land within 3 kilometers of shoreline. These areas are good site for turbine installation because of wind produced by convection due to the differential heating of land and sea each day. Offshore. Offshore wind zone are generally considered to be the 10 kilometers or more from land. Offshore wind turbine are less than turbine on land as their size and noise is mitigated by distance. Offshore installation is more expensive than onshore. Airborne. Airborne wind turbine eliminate the cost of tower as they are located at high altitude. Why wind energy? They are clean, zero emission, not affected by air quality, climate change, reduce fossil fuel depends, and also no fuel price volatility during the renewable. Finally, these are the few modern wind turbine designs based on the orientation of rotor. Thank you. Hope today you all have an insight about the wind energy. Thank you, Manata.